How's the material feeling? Homework going okay? Yes. Okay. Apples. So if it's touchy. Okay, so the question is, when we're talking about finding the standard deviation or the variance, when do we have to square the constant that's being multiplied with the random variable? I'm really sorry. Okay, I'm gonna have to figure something out. I'm just gonna tuck part of my shirt in. Don't judge me. Okay, so if we have the random variable x, so we have the random variable x, and this would have some variance. Some variance x, okay? We could just leave it as this, or we could call this sigma squared, or whatever we want to call it. We might have a situation where we are dealing with some constant times x. So let's look at the farmer's market, and it says the market price for apples is a random variable with a mean of $0.5 and a standard deviation of 0.2. Similarly, for a pound of potatoes, the mean price is 0.3, and the standard deviation is 0.1. And so we're looking at selling 50 pounds of potatoes, okay? So they're all going to go at the market price, okay? So in this case, we're looking at 50 times x, okay? And so the mean, whatever, this is the price of the potatoes, okay? So the mean will be 50 times mu, and then the variance, because it's all banking on this price, the variance is going to be the variance of ax, which is equal to a squared times the variance of x. So you're going to have to square the 50. Versus some other problem. Let me see if there's another problem. This is different from going to the market 50 times and selling 1 pound of potatoes. Okay? Because if we go to the market, so this is selling 50 pounds all at once at the market. Okay, so that's 50x. On the other hand, we might have go to the market 50 times and sell 1 pound of potatoes each time. In that case, we would have x plus x to 50 times. Okay, and so there, your mean would be 50 times mu, but your variance, you'd have the variance of x plus the variance of x all the way 50 times, so you would just have 50 times the variance of x. I don't know if the distinction is clear here. But here, the farmer could make a lot of money or little money, or very little money, based entirely on that day's market price. Okay? So he's selling all 50 pounds of potatoes in one day. So it's going to vary heavily on what the market price is that day. Over here, he's selling, essentially selling 50 pounds of potatoes, but he's selling them 1 pound of potatoes at a time. And so he will not suffer greatly if the price is poor on one day, because overall we're expecting it to even out over the course of 50 days. Okay, so the variance in this case is a lot smaller than over here. And, so there's a distinction between doing X multiple times versus a whole bunch all at once. Okay, and so when you are multiplying by a constant, you've got to square the constant when it comes to the variance. Does that clarify? Okay. Okay, so the homework is getting tougher. These a lot tougher, or should I slow down the? Okay, everyone's nodding their head. All right. Okay. Well, I guess we can adjust the pacing. Okay. So when you're talking about slowing down, what are we talking here?
2 lectures per chapter.
2 lectures per chapter.
Yeah.
Okay.
Like 1.5.
1.5. All right.
Just
Okay.
a little more.
Just a little, spend a little bit more time. Okay, we can do that. We can do that. We can spend a little bit more time. I can also, maybe I'll use my editorial judgment and cut out parts of the chapter that I feel are less important. How's that? Okay, that works also. All right. I don't want to make your life miserable here. Okay. All right. So we'll. So are we feeling okay with chapter 16, or do we need to spend more time there? We're okay. All right. One person will speak for all of you. So. But that's okay. All right. So chapter 17, we are continuing on with probability and all of these probability models. Okay, so just so we don't lose sight of the big picture here, okay, before we did a lot of stuff about data, talking about describing data and all of that. And then we're moving into probability. Probability is all about the probability of unknown events, okay? How likely or unlikely is something to happen? In the future, we're going to merge our understanding of describing data and our understanding of probability to then describe how likely or unlikely are we to observe our data. Okay? Because that's where statistics all comes in. We look at the data and we say, is this likely to happen under these conditions, or is it unlikely to happen under these conditions or assumptions? And so that's where our understanding of the probability comes in. So it's just unfortunate that with probability there's a whole bunch of rules and a whole bunch of different setups and things regarding random variables and all of that. And it's easy to get lost in the formulas and the methodology behind probability rules, okay? So maybe with chapter 17, I will just focus on okay. We'll just focus on the binomial, okay? So I'm going to cut out the geometric model. I'm going to have to, I haven't assigned the homework for chapter 17 yet, so I'm going to go through and just assign stuff on the binomial model. Okay, so we're going to, chapter 17 is about probability models. Okay, and the book lists geometric model, binomial, and Poisson. Okay, this is Poisson, not Poison, and we will skip the geometric and skip the Poisson. And the book only does a very, it doesn't do any justification to the Poisson model, which is actually, which is pretty cool, but probably a little it's not generally covered in a first introductory course to statistics. But the binomial is definitely a key critical one. So this is the one we will cover, and this is the only one that you'll be responsible for in this chapter, okay? So we'll just say if I assigned it from the homework in chapter 17, you were responsible for knowing that much. And we'll do that. Okay. So this is the idea behind a binomial model. Okay. We have something called. I wonder if I should throw out all of this terminology, but there's something called a Bernoulli trial. Okay. But basically, I just have to use the word Bernoulli trial. You can just think of it as a coin flip. A coin flip, but you get to select the probability that it lands on heads. Okay? Coin flip with probability P of landing heads. Okay. That's basically what a Bernoulli trial is. You're just flipping a coin. So generally, when you flip a coin, we're assuming P is 0.5, and you flip a coin, and it lands heads with 0.5, or it lands tails with 1 minus 0.5. Okay? And so with a Bernoulli trial, if we say the outcome is either success or failure. These are the only two possible outcomes when you flip a coin or when you do a Bernoulli trial. It either lands on heads or success, or it doesn't, and we call that failure. Okay? So just imagine a coin. Rather than having heads or tails, the two sides of the coin are success and failure. Okay? You flip the coin, and it doesn't matter what has happened before or what happens in the future. This coin flip, it will either land on success or it will land on failure. And the probability that it lands on success is P, and the probability that it lands on failure is 1 minus P. So the outcome is success or failure. When we turn this into a random variable x, success is labeled 1, failure is labeled 0. And the probability is going to be P, and this is going to be 1 minus P. So I just want to make sure this is okay. Okay. Basically, we're just flipping a coin, and the two sides of the coin, one side is success, and the other side is failure. But it's somehow weighted or something. And so it's not necessarily 0.5, it's P and 1 minus P. Okay, so that's a Bernoulli trial. I could ask, what would the mean, what is the mean for the random variable? It would be P, right? We just do 1 times P and 0 times 1 minus P, and we get the mean is P. Okay? Okay. The binomial model is an extension of that. The binomial model, basically we're saying, okay, rather than just flipping this coin once, which is incredibly not that interesting, because we know it's just going to land on success or failure with probability P or 1 minus P, let's say I flip the coin 10 times, or 20 times, 7 times, it doesn't matter. Okay. We're going to then ask, what is the probability that I get X amount of successes? Okay, so after n coin flips, what is the probability of getting X successes? If I flip the coin n times, what is the probability I get X successes? again, our coin is labeled on one side success and failure. We're just flipping it n times, and I want to know what's the probability that it lands on success x amount of times. So we can explore this. And maybe we'll do this with we'll start off with a probability tree. Okay, so let's say my coin has the success side and the probability of success. Let's, to make it interesting, we won't use 0.5. We'll say 70% chance of success. Okay, so when I flip the coin, 70% chance that it lands on success, then that means the probability that it lands on failure would be what? 1 minus 0.7, 0.3. Okay, simple enough. Let's say I flip the coin twice. And I want to know, if after flipping the coin twice, what's the probability that I get exactly 2 successes? Or I'll ask 3 different questions, okay? What is the probability that I get, part A, 2 successes? It just looked funny. 1 success and 0 successes. Sometimes if you write the same word too many times, it just starts looking funny. Okay, so we'll do this with a probability tree, okay? So the first coin flip, it could land either on success or failure. It lands on success with probability 0.7 and failure with probability 0.3. Okay, if it lands success on the first one, the second coin flip could then also go success or failure, and this would go with probability 0.7 and probability 0.3. Okay, this is a key part of a binomial model, is that every time you flip the coin, the probability doesn't change. Okay, that's how a coin flip works, right? It doesn't care what happened before, so we get 0.7, 0.3 right there. And then even if I get failure on the first one, probability of success or failure on the next one is going to be 0.7, and this will be 0.3. Okay? So what is the probability of getting 2 successes? Okay, so the probability of getting 2 successes, I would have to get success on the first one, success on the second one. So that would be 0.7 times 0.7, 0.49. Part. And then let's just skip down to part C. 0 successes would mean I would have to get failure and then failure. So that would be 0.3 times 0.3, 0.09. So far so good? This is an F. Probability of getting 0 successes after 2 coin flips. It means I have to get failure on both of my coin flips. Okay. And then the last one is asking, what about getting 1 success? Okay? So there's 2 ways. I could get success and then failure, or I could get failure and then success. These are different things, right? So success and then failure would be 0.7 times 0.3, and then failure and then success would be 0.3 times 0.7. Okay? So both of these have 1.7 and 1.3, so I could just say this combines to 2 times 0.7 times 0.3, and I would get 0.42. Okay, and so this would be my probability distribution, okay? So we would say x is binomial, okay, and we're going to say 2 trials, or we say n is equal to 2. That means I'm flipping the coin twice, and then p is equal to 0.7. This is probability of a success. And the probability distribution would look like this. X can take on the values 0 success, 1 success, or 2 successes. And the probability that X takes on that value would be 0.09, 0.42, 0.49. So this would be a binomial random variable. It's just a random variable, but we've determined the probabilities following this set of rules. Is that okay? All right. So let me just extend this. And let's say I flip the coin 3 times. Okay. What is the probability that I get? And let me just rearrange these. 0 successes, 1 success, 2 success, and then I've got to add a 3rd row, 3 successes. So I just extend this to success, failure. Alright, we can see this is starting to get a little tedious. And all of these would be 0.7, 0.3, 0.7, 0.3. Okay, I know those of you sitting in the back, you can't read what I'm writing, but just, it's gone on. Success, failure, so on and so forth. Alright. So if I flip the coin 3 times, what is the probability that I get 0 successes? What is my answer there? I'd have to get failure, then failure, and then failure. So that would be 0.3 times 0.3 times 0.3. And that would be 0.027. I'm hoping I'm doing my multiplication correctly. Is that okay? Okay, 1 success. That could happen in a few different ways. I could get failure, failure, success, failure, success, failure, or success, failure, failure. Okay, these are the only 3 ways I could flip the coin 3 times and get exactly 1 success. Are we in agreement there? Okay, so each of these have 2 failures and 1 success. So the probability of success is 0.7. That's going to happen 1 time. And I have to get failure twice. So that would be 0.3 times 0.3, and I'm going to square that. Okay, so each line is basically, this one is 0.3, 0.3, 0.7, this is 0.3, 0.7, 0.3, and then this is 0.7, 0.3, 0.3, okay? But basically, because multiplication is, what is it, cumulative? No, commutative, you can change the orders and it doesn't matter, okay? So I'm just going to say each one has 1.7 and 2 0.3s. But how many different ways are there? It could happen 3 ways. And so my total probability here, 0.063 times 3 is 0.189. I hope I'm doing that correctly. And that's what we have there. Yes?
If you were to do a negative 0.7 times 0.3, would you get the same answer?
Yeah, except it's 0.3, because it's failure, failure, success. So it'd be 0.3 times 0.3 times 0.7. Yes, and you would, here you'd be 0.3 times 0.7 times 0.3 plus 0.7 times 0.3 times 0.3. And if you add those up, you should get exactly 0.189, okay? Or whatever this is, okay?
That's right.
It's correct, okay. Still got it, all right. And so for 2 successes, I would have success, success, failure, SFS, and FSS, okay? And so each of these I would have 0.7 twice, 0.3 once. Is that okay? And 3 different ways for that to happen. And I can't do this in my head. 0.441? I don't know. Something. Somebody save me.
That's right.
Is it? Okay. Is this okay? So 0.7 square, and then the last one would just be, it has to be success, success, success. So I'm just going to do 0.7 cubed. Okay, and I don't know. I give up. Something else. Something else. 0.343. Okay. So here is our probability distribution for binomial random variable. And so our x can take on values 0, 1, 2, and 3 with probability 0.027, 0.189, 0.441, and 0.343. Okay. So before, okay, so let's say I extend this and I say I'm going to flip the coin 6 times. And I ask, what's the probability that I get 0 successes, 1 success, 2 success, 3 successes, and then I would also have to add the lines for 4, 5, and 6 successes, right? Because if I flip the coin 6 times, I can get anywhere between 0 and 6 successes. And we can see that to answer this question, it would be very, very tedious to try to draw the full tree. Okay? But I'm hoping that when we did the tree for 3, we started to see a pattern here. Okay? Okay, so what is the probability that I get 0 successes? Well, that would mean I would have to get failure 6 times. So that would equal the probability of 0.3 raised to the 6. Okay? So whatever that is, that's what we would get. B, to get 1 success, that means I had to have how many failures? 5 failures. Okay? So there's probably a whole bunch of different ways, or there is a whole bunch of different ways for us to get 1 success and 5 failures. I don't care if the success was the first flip, or the third flip, or the 6th flip. I just need at least 1 success in there. Okay? So I would have 0.7, that's the probability of a success. That would have to happen 1 time, so that I can just raise that to the 1. And how many times would I have to have a failure?
5.
5 times. So I'd have 0.3 raised to the 5. And then I have some number here, which is how many ways can I have one success out of 6 trials? Okay. So when we did 3 coin flips, we said there was one way, or 3 different ways to get one success out of 3 flips. Okay, and so we just have to figure out this number. Okay, we'll come back to that. For part, the probability of getting 2 successes, I would need 2 successes and how many failures? 4 failures, because we had a total of 6 coin flips. So the probability of success is 0.7. That would have to happen twice, so 0.7 times 0.7. And the probability of failure is 0.3, and that would have to happen 4 times. And then again, we have some mystery number, and this would be, how many ways can I arrange? How many ways can we have 2 successes out of 6 trials? Okay, and then so for to get 3 successes out of 6, what would I have? I would have 0.7 raised to the 3, and I would have 0.3 raised to the 3. And then also some mystery number here. Is that okay? Alright, so 1 success, 5 failures. If I do 6 trials, how many ways can I get 1 success? Okay, well, this one is not so bad. I could have success. There's 1, 2, 3, 4, 5. There's 6 different ways. Failure, failure, success. Basically, I'm just changing the position of the success, okay? But then it gets a lot more complicated for having 2 out of the 6, okay? So this is where we bring in something called the choose, all right? This is combinations, and we would do 6, choose 1. This is read as 6, choose 1. And over here, we want 2 successes, so this we would use 6, choose 2. So 6, choose 1 for there, and for this one we would have 6, choose 2, and over here we have 6, choose 3. Okay, so this is, there's a few ways we could get the choose. The easiest way is just to find the choose function on your calculator. Maybe on your calculator you have a button labeled NCR, okay? Depending on what kind of calculator you have, it might be over it's probably a second function. If you have a TI, you probably have to hit a math or probability button, and then you can go through the menus to find NCR. Okay, so you might have to hit, if you've got a graphing calculator, you might have a PRB button, and you click that, and you might find NCR somewhere in there. If you have a regular one, you might have a PRB button somewhere on there, and then you can use your up, down, left, right arrow keys to find NCR. And so you would enter this as 6 NCR 1, and then when you hit enter, it'll tell you 6. And I think if you do 6 NCR2, it'll tell you 15, right? Yes. So, and then 6 NCR2, and then 6 NCR3 is 20. Okay. Are our calculators working? Yes.
So what exactly is the choose determining?
What is it determining? It's
Number of ways.
It's the number of ways. If you have 6 positions, okay? So just imagine if you have 6, 1, 2, 3, 4, 5, 6, okay? 6 spots, and you're going to throw one thing in there, okay? One success. How many different places can you put the successes? So 6 choose 1, there's 6 places where the success can go. Okay? 6 choose 2, let's say I'm going to throw in 2 successes. Okay? Now the success can go there, or it can go there, or whatever. How many different arrangements does it go? And we don't care if this success goes, if this success goes over here and this one goes over there, that's the same as them being swapped. Okay? I don't care. These successes don't have names and personalities. There's just the outcomes of coin flips. So okay, they're, you know, the first and the second. Okay, so how many ways can that happen? That's 6 choose 2. If you care about the combinatorics or whatever, the formula for NCR is given by n factorial divided by r factorial times n minus r factorial. And I probably regret my choice of letters because the book uses x rather than r, but whatever. Okay. So it has NCX rather than r, but so just replace the x, r with the x. And I don't know if I should get into the explanation. The explanation is not necessary, okay? The n factorial comes from all the different ways you can arrange the seats, and then the r would be all the different ways you can arrange the s's, and then the n minus r factorial would be all the ways you can arrange the empty seats, okay? That's how it works, but not necessary for this. Okay, so anyway, we have this, so now that we can figure out how many ways can I have one success out of 6 trials, I can replace this with 6 choose 1, which is equal to 6. How many ways can I have 2 successes out of 6 trials? This I'm going to replace with 6 choose 2, and then over here I would put in 6 choose 3. Okay, so let's break this down to a generalized form so that we can figure this out for any binomial situation. Okay, so we would have n trials, or n coin flips. P is the probability of a success. And x is the number of successes that we want to calculate the probability for. Okay? It's the number of successes we are interested in. So the probability of getting x successes would be equal to the probability of the success, p, raised to the x. It has to happen x times. Okay. What's the probability of a failure on a single coin flip? 1 minus p, right? Okay, that's how I'm getting the 0.3 over here. How many times does that have to happen? If I have a total of n coin flips, and x of them are going to be successes, how many are going to be failures? N minus x. Okay. And how many different arrangements are there? And choose x. Okay. You can, well, you'll have your note sheet, but it's rather simple. Just say, just as you're writing this out, just say, as you're writing n choose x, say, I have n trials and want x successes. And then when you write p to the x, say the probability of success is p, and we want x of those. So that, and over here, 1 minus p to the n minus x, probability of failure is 1 minus p, and we need n minus x of those. So that's how they all go together. So we'll talk this through for, let's do f here, okay? So what's the probability of getting 5 successes out of 6 flips? Let me just make sure I'm doing okay on that. Alright, so here I have 6 flips and I want 5 successes. The probability of a success is 0.7, and how many of those do I need? 5. The probability of a failure would then be 0.3, and how many of those do I need? 1. Okay. So this is the probability of getting 5 successes out of 6 coin flips. All right. So for calculating the mean and variance, or mean and standard deviation, of a binomial variable. Okay. Well, at the end of the day, when you create the probability distribution, you'll get each outcome x and the probability of getting that x. Now you could do the calculations for the mean and the variance the way we did for all of the random variables in chapter 16. But we have shortcuts, okay? We have shortcuts for the binomial. The mean is going to be n times p. And that makes sense. If I'm flipping the coin 100 times, and the probability of a success on one coin flip is 0.7, after 100 coin flips, I'm expecting around 70 successes, more or less. The standard deviation is equal to the square root of n times p times 1 minus p. Variance would be the square of that. Okay. So in these examples, I've done something. I just said we're flipping a coin labeled success and failure, where the two sides of the coin are success and failure. But the truth is the binomial can be applied to any situation where there's only 2 possible outcomes for each trial. It could be we're looking at a basketball player, and we ask if he takes 10 free throws during a basketball game, what's the probability he makes exactly 8 out of 10 free throws? Okay? Every time he takes a shot, it either goes in or it doesn't. Okay? So there's only, this happens or it doesn't. So there's only 2 possible outcomes. And then if we assume that every time he takes a shot, it's a random outcome of whether he makes it or not, and the probability is the same, then we could use the binomial probability, binomial distribution here. Okay. But that's an assumption you have to make, that every time he takes a shot for a free throw, that the probability of him making the shot remains constant. That may be up to debate. Okay. It could be any time you play a game of random chance. So if you go to Las Vegas and you play roulette 20 times, the probability that you